All right, good morning. Welcome back. Hope we had a great weekend. So we start again today on page 32. We will take a quick look at our calendar. Before we take a quick look at our calendar, we'll look at the whiteboard over here. Today is the first meeting of the math club of this semester. So if you have any interest, come on by today at noon. You can come a little bit late. You can grab some lunch and bring it here and eat. Very informal. So come by today if you have any interest in math club. So today in calculus, let's see what's happening. So project number 5 is now assigned. So grab one from the table. Is there anybody that doesn't have, this whole table over here doesn't have? If there are extra projects 5s, can we shuffle them up this way? So everybody grab one and then bring some extras. We need 3. Okay, thank you. There should be enough. Okay, so project 5 is assigned. It is due 1 week from today, Monday of next week. All right. Project 5 is naked derivative practice. I'm not going to try to couch it in any other terms. It's just practicing all of these complicated chain rules in the midst of all the new derivative rules that we've learned over the next few weeks. All right. So lots of practice, and that's due 1 week from today. I handed back the quizzes, but over the weekend I did not grade the projects you just turned in. In fact, I haven't touched them, so I have stuff to do on my end. I'll get them back as soon as I can. At some point this week, they'll come to you. On Friday, what's happening here? Quiz number 5. The point of having quiz 5 Friday is that I can give it back to you on Monday, which is our review day for the test. And then Wednesday, we have our second test, okay? It will be here before you know it. Do you guys remember heading into the first test, there were some sample test problems in the packet, and then I made those videos on YouTube you could look at of me working through those problems. So the same thing is happening in packet 2. If you hunt around a little bit towards the back of this packet, you will find a whole slew of sample test problems. I can remind you how to find the videos on YouTube, but they are there. So do a little bit of hunting and should be able to find it. All right, so that is all of that. So let's come back here to page 32. And on page 32, it talks about the basic plan for today is to learn a few new derivatives and then a general formula for differentiating the inverse of a function. And this is going to be the common theme for us today. You guys know a lot about the sine function. You know a lot of calculus things now about the sine function. So the question is, well, what about the inverse sine function? Are there some calculus things that we can figure out about the inverse sine function, given that we now know some things about the sine function? And let's see, so e to the x, you guys know a lot of calculus things now about e to the x. What's the inverse of e to the x? Not the derivative of e to the x, what's the inverse of e to the x? Is the natural log, right? So today we're going to see how to find the derivative of the natural log, but we can only do it because we know a lot of stuff about e to the x already. So that's kind of the theme. You guys know some things about some functions. We're going to look at the inverses of some of those functions and try to get some calculus knowledge out of that. So I'm going to jump down to number 3, where we just fill in the punchline, the derivative of ln of x, and then we'll go back and prove it, trust me. But let's just get to the punchline first. So either from your reading or if you happen to know it from before, what is the derivative of ln of x? What is it? What is it? It's not e to the x. It's 1 over x. So if you did the reading, you would have found this formula. We'll prove it, but the derivative of ln of x is 1 over x. Nothing more, nothing less. So then what if it's the chain rule? What if it's not ln of x, but ln of stuff? Okay, so 1 over stuff, we buy that, right? 1 over stuff, and then I'm going to tack on in green because every time we have the chain rule, we tack on the same thing in green. In English, what is it? Derivative of stuff. Right. So our new rule, derivative of ln of x is just 1 over x, nothing more and nothing less. And then we can, every time we have a new derivative rule, chain rule comes out and just says, okay, do what you think you should do. Instead of 1 over x, it's 1 over stuff, but then times the derivative of the stuff. So let us try. I'm just going to make one up right here real quick. Can you guys find the derivative of ln of x to the 8th minus 4x? Can you find the derivative of that? I just made that one up so you won't find it on the packet. And check with your neighbors. Okay, how do we start this one? 1 over the stuff, 1 over all of that. Don't put a derivative down here. It's not 1 over 8x to the 7 minus 4. It's 1 over the stuff. Copy it once every time. I'll tack it on here in green. What gets multiplied? Derivative of the stuff. So out here, 8x to the 7 minus 4. What's missing? Parentheses. That whole thing in green is one thing. So it's that. Does that mean the 8x to the 7 minus 4 is upstairs or downstairs? It's upstairs. So just want to be clear. This is, in some sense, our first derivative rule, which intentionally throws something into the basement, right? We had ln of x to the 8th. All of a sudden, x to the 8th used to be fine. Now it's downstairs. It moves something downstairs. But the chain rule doesn't care about that. Chain rule doesn't put anything downstairs. It just puts it next to the function, which means on top. So if you want, put that on top, and you've got your one fraction. That's it. Can you guys try part B down here at the bottom? Y equals ln of x. Find the derivative of that. And again, look around. If you're starting and your neighbor is not, give them a hint. Okay, here we go. Y prime equals, what do we get? 1 over ln of x. That's 1 over the stuff times 1 over x. That's times the derivative of the stuff. I think probably if we have fractions, we're going to want to mush them together just like Iris has suggested. The only reason we put the x in front is just so it doesn't look like it's part of the ln. It's not inside of the ln. That's it. Any questions on that one? Okay, what about part A? Ln of x squared. First, I have a question. Can we bring the 2 in the front? Isn't that one of our properties of logs? You can bring the 2, bring the power. Yeah, so Topher is pointing out the difference between that thing and that thing, and they are fundamentally different. Only one of them has that nice property that we can apply. So just pointing out, they sound the same when you say them, but they are different when you write them. It's the first one up here that you can bring the 2 in the front if you were so inclined, okay? You can't move this 2 down here anywhere. So just want to highlight one subtlety of one of the properties we've been talking about. Okay, so here, what I see is some stuff squared. I can handle stuff squared. So can you. Find the derivative of part A and check with your neighbors. Okay, let's get our answer here. Y prime equals, what comes in the front? 2 times ln of x. We copy. What's the new power? 1. You don't need to write it, but I will. Times, I'll put it in green again. What's the derivative of the stuff? 1 over x. You could use the product rule. Was it the same as this? Same as this thing? That sounded a little bit different than what we got. All I got was I think it's a 2. I think it's 2 times that fraction instead of squared. What's that? Oh, yeah. Plus. Yeah, plus. Right. Okay. Yeah, that's what we have here. Okay, so that is fine. Just for kicks, maybe this isn't how you guys get your kicks, but I'm interested in the graph of this function right here in part B, ln of x. Okay, just think about ln of x, not 2 of them, just y equals ln of x. Can you guys draw it in the air? This is a function that we looked at last time. Ln of x never hits what? Never hits the y-axis, right? X equals 0, so it's got an asymptote. It's way down there at minus infinity, and then it comes up. It hits one nice point. Is it 1, 0, right? It's one nice point, and then it grows forever. And how does it grow? Really slowly, right? It does make it up to positive infinity, but you better have a lot of time to wait for it. So now we have ln of x. Okay, so first of all, if we plug in if we plug in an x value that's between 0 and 1, so this is the part that was near the y-axis. Can you guys picture that? That was the part that was going down to minus infinity. So if I plug in a number between 0 and 1, then ln of that number is something negative. And then there's the other ln sitting in the front. And when I try to take ln of a negative number, ln breaks down. ln doesn't exist for the negatives. So instead of getting very close to the y-axis, I feel like this guy is going to start at x equals 1. Instead of starting at x equals 0, it's going to start at x equals 1. And then how is it going to grow? Well, if ln of x grew slowly, and this is ln of x, this is going to be like snail-like in its progress. I mean, like seriously. So, so real quick, I'll put it up on GeoGebra here. F of x equals ln of x. All right, so there it is. So first of all, what do we see here? Does it get close to the x-axis? No. I mean, it starts at x equals 1. It's that thing that I described, just because ln doesn't exist for those negatives. Okay, and then, okay, it doesn't hit the nice point that it hit before. Can you guys figure out what that point is? Is that easy to figure out? Should it be E? Let's see. So I'm going to look. I mean, it's about 2.5 something. So maybe it's E. So if we come back here, if you put E right there, how much is ln of E? Is 1. And how much is ln of 1? 0. Perfect. So the x-intercept is now E, comma 0. Super. And then how does it grow? Well, it looks like it's growing slowly, but I'm not, you know, like it doesn't seem like it's like super slow. So let's just pull to the right. I just want to see if we can get it to come up here to 10 or something. So let's pull this to the right and pull it to the right and pull it to the right. Okay, we just got to 2. And then we're still pulling to the right. And what are these numbers? E to the 9th. What word is that? Is there billions? Okay, so at 2.5 billion, we're around 3. So it does grow forever. It does get up to infinity, but it takes a long time. Long time. Okay, so let's come back here. All right, so I promised you that we would prove this formula here, this 1 over x. And so on the test, I'm just going to ask that you use that formula 1 over x and that you can do the chain rule like we just did. I'm not going to ask you to prove it, but I will say kind of the point of us doing this proof here is that the technique we're about to do is something very general, and you can apply it to finding the derivative of any inverse function. So we're actually going to do this thing twice in 2 different contexts today. Again, it's not something I'm going to ask you to replicate, but in some sense, I think it's the most important thing for today. 5 years from now, if you need to know the derivative of ln of x and you've forgotten it, you're going to go look it up. I mean, it's not a big deal to just find it. But like this idea that you can figure something out, you can figure out what the derivative is, I think is a powerful idea. So here's what we're going to do. The goal is to find the derivative of ln of x. We've already spoiled, the punchline is here. It's 1 over x. But let's get there. So first, do we believe this equation is true? E to the ln of x is exactly the same as x. That was one of our nice properties from last time. So I'm going to copy that equation again. E to the ln of x is equal to x. But in front of both sides, we're going to put a derivative symbol. So I'm going to take the derivative of both sides of that equation. So if they were equal before, I can take a derivative and they still be equal. Okay, let's do the right-hand side first. It's easy. What's the derivative of x? 1. Now we're going to do the derivative of the left side. E to the ln of x. Okay, it is tempting to, instead of e to the ln of x, write what? But yeah, we're going to do that. But it's tempting to do what at this point? E to the ln of x. You see it. What do you change it to? Change it to x. But if you do that, you just get x equals x, 1 equals 1. And it's not going to help us. So leave it there, even though it's very unnatural for us to leave it there. But Topher points out we could think of this as e to the stuff. You guys know how to find the derivative of e to the stuff. What's the derivative of e to the stuff? E to the stuff times derivative of stuff. That was one of our first chain rule examples. Okay, so let's apply it. E to the ln of x, what's the derivative? E to the ln of x times, I'll put it here in green, And I'm just going to put it in symbols. Derivative of ln of x, the stuff, yes? Okay. You know what the derivative of ln of x is because we had the punchline there. But at this point, we're pretending we don't know the answer is 1 over x. What we're trying to do is figure out what the derivative of ln of x is. That is to say, we're trying to figure out what this green thing is equal to. So if I asked you to solve this equation for the green thing, what would you do to both sides? Divide by this e to the ln of x. Just put it under there. Yeah? So we'll get our answer then. Derivative of ln of x must be equal to this one divided by e to the ln x. Do we see it? And now we're going to replace, this is 1 over, what is e to the ln of x? It's x. So the derivative of ln of x must be 1 over x. Okay, so again, I'm not going to ask you to replicate that on the test, but it is nice that we can just do this technique and figure out what the derivative is. And in some sense, this is, I would say, more powerful than the proof. We looked the other day at the derivative of sine. What's the derivative of sine x? It's cosine x. And we proved it by writing out the long limit definition, right? And we did all this stuff, and we had a couple of crazy limits that popped up that were important. And we didn't do any of that here. So first, it's nice that we didn't have to get into all the limit definition of the derivative. And the other thing is, we kind of knew the answer was going to be cosine. Like we looked at a graph and we did some guessing, and we figured that maybe the derivative of sine is cosine. So we kind of had some idea as to what to expect. But here, you don't have to know anything, right? You just follow the bouncing ball and the derivative will pop out. It requires no graphing. It requires no intuition. It's just this nice little process that if you have information about one function, you can get information about the inverse of that function. Okay, so that is that. Let's move on to the next page. And we're just going to take a real quick look at GeoGebra. So I'm going to start from a clean sketch in GeoGebra just like this. View the grid. All right, so I want to graph ln of x, regular ln of x. This is now the speed demon. Like we didn't realize how fast this thing grew until we saw ln of x. So that's fine. And then here's what I want to know. Is this function increasing or decreasing? Increasing, which means its derivative should always be what kind of a number? Always be positive. 1 over x was our derivative. Is 1 over x positive out here? Yeah, for all these positive x's, absolutely. 1 over x is positive. So that makes sense. And more than that, let's take a point. I'm going to put the point. We've done this before. You can check out the video if you want to see the details, but we put a point there. And then I'm going to come in here and go to my tangent tool. It says select a point, and then select the function. So I click on the point, click on the function, it draws my nice little tangent line. I've got all these tangent lines here. Super. Suppose that I go here to x equals 4. According to what we just found, the derivative is 1 over x. So what's the slope of that tangent line at x equals 4? It's 1 over 4. And you can see it out here. They wrote the equation of the tangent line. It's 0.25x. That's the slope. It's 0.25, 1 over 4. If I go to x equals 10, there. What's the derivative at that point? 1 over 10. And you can see the slope of this line is 0.1. And does 1 over x do exactly what we think it should do? That is, get smaller as x gets bigger. Yeah, that makes good sense. What if we go to some fraction? What if I go to x is a fifth? I'll come in here, maybe say right. Right. Okay, we're having trouble. Let's spread this out. So what if x is a fifth? Something around there, 0.2. How much is 1 over x when x is a fifth? It's 5. Does it make sense that the slope of these kinds of points is big, like 5 is a pretty steep slope? So 1 over x, it gets smaller as you go to the right, but it also gets really big for these kind of decimal x's down here. That's exactly what it should do, right? So 1 over x is perfectly reasonable. It's not just this rule we make up. It jives with the behavior of ln of x. One other quick thing here, just going to point this out, and if you want to explore, I'm happy to to help you explore. Take a look at the x that I've selected here. Sorry, take a look at the y. How much is the y? You can read it over there on the left. 2.3 is that y value. Now this tangent line goes in and it hits the y-axis somewhere, right? And you can see the equation of the tangent line. What is the y-intercept? 1.3. Well, that's interesting. The y value of the point on the curve is 2.3, and the y-intercept of the tangent line is 1.3. Let's see. So what if I come over here? We'll just pick that guy right there. What's the y value on the curve? 1.42. The y-intercept of the tangent line? 0.42. What's that, Jeremy? Is it x units less? So you think it's some, so I agree it's less. So how much less is the y-intercept? It looks like it's always one less. You can take a look. And it's true, and it's actually true for a really good reason. Suppose that, that we just focus on this point right here. I'm going to come down here, and I'm going to draw this thing to the x-axis right there, to the y-axis. And I'm going to call x this distance. So far, so good. And then what I'm going to do is look at something else. All right, so then I'm going to copy that same x up here. And what I want to do is go from here down to the y-intercept. Now, what did we say it looks like the difference is there? It looks like it's a 1, right? It looks like they're always 1 apart, whatever the y was compared to the y-intercept. Okay, forget calculus now. Suppose that I just look at that tangent line, and I ask you to find the slope, looking at this little triangle here. Slope is change in y over change in x. How much is the change in y over the change in x? 1 over x. What's the derivative of ln of x? 1 over x. So it makes perfect sense that, that this guy right here has to be a distance of 1 because we need it to be a 1 over x, change in y over change in x. Anyway, I think it's cool. All right, so let's come back to here and let's spoil the punchline again. So we're going to find the derivative of inverse sine of x, and I'll just share with you the answer unless anybody happens to know. Anybody know the derivative of inverse sine of x? Okay, so we'll put it here, 1 over square root of 1 minus x squared. It's almost so obvious that we don't want to even write it down. So 1 over the square root of 1 minus x squared. That's the derivative of inverse sine. Why? We'll prove it in just a few minutes. Let's just accept it for right now. And just to make sure that we're all okay, I will point out, and we'll look at this again in more detail next class, but on the very first page of this packet is this derivative formulas reference sheet, which right before the test you're going to rip off and use on the test, in addition to the one piece of paper you're going to make of your own choosing. And I will just point out that all the derivative rules we have seen so far are here, including the one that we just saw. First thing today, derivative of ln of x is 1 over x, and then the one that we just said there, 1 over root 1 minus x squared. All right, so you'll have it. This is not like a test of who can memorize the most like erudite formulas that you'll never use. I'll give you the formulas, but I want to see that you can use them. So let's come back to where we were, which I think is there. Okay, can you guys fill in the chain rule version of that new rule? This is now, instead of inverse sine of x, it's inverse sine of stuff. So stick on the derivative of inverse sine of stuff. Okay, how does it start? 1 over square root of 1 minus stuff squared, right? Instead of x squared, it is stuff squared. And then in green, chain rule says times the derivative of the stuff. That's it. Every time you have a new derivative rule, chain rule comes in and gives you a whole brand new class of things that you can find the derivative of. And to be clear, is that derivative of the stuff upstairs or downstairs? It's upstairs. Derivative of the stuff is always upstairs. Doesn't care what the specifics of the rule were that you just applied. Okay, so we'll prove that one. We're not going to prove the one for inverse tan, but it's something similar. So it turns out the derivative of inverse tan of x is 1 over 1 plus x squared. It looks similar, but there are some differences. So if it's 1 over 1 plus x squared, can you guys fill in the blank over there? Again, using the chain rule. Normally it's 1 over 1 plus x squared. So what is it now? 1 over 1 plus stuff squared. And in green, derivative of the stuff. Okay, so let's see if we can apply these two rules here to find the derivative of the inverse sine of 5x over the arctan of x cubed. Ugh. All right, first and foremost, what rule is this? This is quotient rule. Right? That is a fraction before it's anything else. So take maybe 90 seconds or so, see if you and your neighbors can agree. Don't worry about simplifying it. I just want unsimplified version, do only the calculus to find this derivative and check in with your neighbors. Okay, so do we want another few moments? Okay, another few moments. Don't worry about simplifying, just see if you can get the calculus. Okay, so let's come back together and see if we can get to the same place. So we said quotient rule. The very first thing I do when I see quotient rule is which piece is the bottom squared? Because I feel like I'm going to forget it in the midst of doing all the complicated things on top. So it's the bottom squared. Just to be clear, you cannot make this x to the sixth. You're not squaring the x cubed, you're squaring the whole arctan, all right? So don't be tempted into multiplying those powers. Okay, so let's see. Does the quotient rule start with the bottom or the top? Bottom, then times the derivative of the top. So we copied the bottom, it's there. Times, and now what we need is the derivative of the top. So I'll circle this thing in blue. We're looking for the derivative of inverse sine. So we have seen, it's up here in blue, 1 over radical 1 minus stuff squared. So this becomes 1 over radical 1 minus something is squared. What is the something? 5x, that's the stuff. Okay, should be 1 over root 1 minus x squared. Now it's 5x squared. But then in green, times the derivative of the stuff. The derivative of what's in the parentheses is 5. So that's that part. Does the quotient rule have a plus or minus in the middle? I say minus. Minus the, let's see, the top. So I copy the top times the derivative of the bottom. So I'm going to circle the bottom in red, and then we'll write its derivative in red. Derivative of arctan, we just saw 1 over 1 plus stuff squared. So I can copy that pattern, 1 over 1 plus something squared. What's the something? X to the third. See it? That's the something. This guy you can make x to the sixth. Okay, but in green, times the derivative of the stuff in the parentheses. What is the derivative of this x cubed? 3x squared. That's it. I don't hate you. There's not a whole lot that I see that we can do. I mean, maybe you can make, I mean, it's going to look worse, to be honest, but what you could do, you could make the, here, I'll kind of highlight here. So you can make all of this one fraction instead of being a times, times, times. Just make it one fraction. You can make this guy one fraction instead of being times, times, times. And then when you have two fractions subtracted, you can combine them. What do you need to find? Common denominator. So that would be kind of messy. But anyway, you could make then the whole thing upstairs can be one fraction. And then it's a fraction within a fraction, so you can make it one elegant. So you can do that if you decide you're going to split this thing up into two fractions. So if you split this up into that guy and then separately that guy, then absolutely in one of them you can cancel the arctan. So that is that. Just curious here, so let's come back here and see what happens if we go to Wolfram alpha. So let's see, derivative. Okay, derivative of. All right, so what was it? I don't understand why ours is not one of the top hits, but so what was it? Inverse sine, so maybe I'll type it as arcsine of 5x divided by arctan of x to the third. Let's see what Wolfram alpha thinks of this monstrosity. How's that look? Okay, wait, so ours, did we have this on the bottom? Okay, did we have a radical 1 minus 25x squared? It might be a little bit misleading the way they've written it. I mean, we know what it's supposed to say, and that's what they meant it to say, but it is a bit difficult to decipher that. Okay, so did we have a radical 1 minus 25x squared on the bottom? Yeah, we didn't write it that way, but we could have squared the 5x. Okay, so that's fine. And then what else is going on here? Okay, so I have an x to the 6 plus 1. Do we have that? X to the 6 plus 1, that's the red thing. Okay, and then upstairs, let's look at the first one. 5 times the inverse tan. Do we have that? 5 times inverse tan. Up still, all they did is make it one fraction. And then over here, there's a 3x squared times the inverse sine. 3x squared times the inverse sine. So they didn't go any further. They just basically made the two fractions, and then that's it. Did they? Let's see. All right, so there's a graph of something, I don't know, and then more graphs, I don't know. Oh, alternate form. Oh, there you go. Yeah, this is what I was imagining. That's how you make it all one big fraction. I told you it was going to look worse than it did. All right, so there you go. Okay, let's come back here. So at the moment, I have just completely bullied you into this formula that we wrote, the 1 over radical 1 minus x squared. So let's see if we can figure it out. Now, figuring this one out is going to be tougher than figuring out the ln of x. So I'm just warning you beforehand. It's going to be a little bit tougher. So, and then we're actually going to get to the answer pretty quick, but it's not going to look like this. And so about half of the work involved in this problem is going to be to rewrite the answer that we get so that it looks like the one we're expecting. So let's give it a shot. When we looked for the derivative of ln of x, we first started off by writing this identity right here, that e to the ln of x was x, okay? We're going to do something quite similar. We're looking for the derivative of inverse sine. Pretend you don't know what it is. And so we're going to write an equation that brings the sine function into this. We're trying to bring the other function, the inverse, into it. So first, do we believe this? Sine of inverse sine of x is x. Cancel. Okay, so we're going to take that equation and we're going to take a derivative of both sides. So I will copy that whole mess right now. And then in front of both, we're going to put the d dx notation. Okay, let's start on the right-hand side. That's the derivative of x. Fun. Super. Now let's do the left-hand side. In English, I see sine of some stuff. I don't care about what the stuff is. What's the derivative of sine of stuff? Cosine of the stuff. And then times the derivative of the stuff. So we're doing cosine of the stuff. So cosine of what? Sine of x times, I'll put it again in green, the derivative of the stuff. What is the stuff in this case? Sine of x. Okay, so that's just our basic derivative of sine rule. And the goal of this problem is to find the derivative of the inverse sine. Well, look, it's sitting right here in green. I just have to get it by itself. The derivative of the inverse sine. We're pretending we don't know it's got that radical in it that we wrote down. We're just trying to figure it out. So what should we do to both sides to solve for this green? Divide by this cosine part. Okay, easy enough. So the derivative of inverse sine of x is equal to 1 over cosine of inverse sine of x. Done. That's the derivative. Okay, so what were we expecting it to be? This 1 over the square root business. That's what I was expecting. Instead, I get this 1 over cosine of inverse sine of x. So it turns out those two are exactly the same. And if you were to graph on your calculator 1 over radical 1 minus x squared, and then separately graph 1 over cosine of inverse sine of x, they'll be exactly the same. But it turns out people generally don't write it as we did in black. They generally write it like we did down here in blue. So the calculus is done, but we're going to do some pre-calculus stuff to try to get that black thing to look like this blue thing, okay? All right, so here we go. The question is, what is cosine of inverse sine of x? If you believe the thing in blue, what is the answer? Is that square root of 1 minus x squared? That's the goal, right? I'm really hoping that cosine of inverse sine of x turns into this denominator, radical 1 minus x squared. So how about we do this? I'm going to give a name to this thing in here. I'm going to call it theta. And so now the purple has changed. It's now asking me to figure out cosine of what? Theta. Okay, so all we did was substitute. So cosine of theta is really the goal. All right, fair enough. Let's take this blue equation. If theta is the inverse sine of x, then you can actually write the sine of something equals something. Sine of what? Sine of theta is x. You buy that? If theta is the inverse sine of x, maybe take the sine of both sides. So sine comes on the left, cancels with the inverse sign on the right. So we get that. Okay, so sine of theta is x, which I'm actually going to write as a fraction. I'll write it as x over 1. And then I'll ask us to remember some SOHCAHTOA stuff. What is sine defined to be? SOHCAHTOA is opposite over hypotenuse. Buy that? All right, so I'm going to draw a right triangle. Put it over here. I'll put a theta someplace. It doesn't matter which acute angle. Just put a theta somewhere. And we have over there opposite over hypotenuse. So what is the opposite in this triangle? It is the vertical. And what is it equal to according to that fraction over there? It's equal to x, right? We want the opposite to be x and the hypotenuse to be 1. That's what that says. So the opposite is going to be x and the hypotenuse is going to be 1. So far, so good? Okay. Remember again, the goal is this thing in purple. Cosine of theta equals. That's what we're after. Again, thinking SOHCAHTOA, what is cosine? Adjacent over hypotenuse. Can you look at this triangle and figure out what the cosine of theta is? It's adjacent over hypotenuse. It's adjacent, which is this blank, over 1. So what do we have to do? We have to fill in the blank. And what most famous of all theorems in mathematics is the one we'll use to fill in the blank is the Pythagorean theorem. So I'm just going to put it. I'm hoping that you guys buy it. But if you use the Pythagorean theorem and figure out what this side has to be, it's the square root of 1 minus x squared. So fill in the details of that later on. I think you guys can handle that. It's Pythagorean theorem. So give it a shot later on. And we're there. Remember the goal was cosine of theta. Cosine is adjacent over hypotenuse. What's the cosine of theta? Root 1 minus x squared over 1. So cosine of theta is really just radical 1 minus x squared. And then that thing was the cosine of theta. It works out. Okay, so so far we've done two derivative calculations. We've figured out the derivative of ln, and we've just figured out the derivative of inverse sine. And there are some commonalities here, actually. So first of all, they were both fractions, right? What's the derivative of ln of x? 1 over x. What's the derivative of arc sine? 1 over radical 1 minus x squared. So they're both fractions. What's in the top for both of them? Is 1. Okay, that's interesting. So it's 1 over. And then on the bottom, on the one, it was x. On the other, it's this kind of funny square root of 1 minus x squared. So it turns out there's a way to do this in general, a way to find the derivative of any inverse function. And we're going to put this on the next page. I'm skipping number 10, and I'm skipping number 11, and we're just going to get to the punchline again in 12. And in 12, it asks us to find the derivative of f inverse of x. You guys have already seen two derivatives of inverse functions today. And every time it ended up being a fraction, and what was upstairs? 1. So that's always upstairs. We'll put it here. Okay. Now what goes downstairs? I'm going to go back and look at the previous question. We're going to figure out what this formula is. Okay. Looking at the pre-simplified version right here, the derivative of inverse sine turned out to be 1 over cosine of inverse sine of x, all right? Why was there a cosine there? Where did cosine come from? It was the derivative of sine, right? So it wasn't the derivative of inverse sine. We started with inverse sine, but then we quickly traded it for sine because we know stuff about sine. So downstairs was this derivative of sine function. Okay, let's come back here. I'm looking for the derivative of f inverse. So downstairs shouldn't be the derivative of f inverse, should be the derivative of f. Okay? We wanted inverse sine of x in here. But somehow downstairs, it wasn't the derivative of inverse sine, it was the derivative of just plain old sine. So down here goes f prime, derivative of plain old f. Okay, let's come back to our previous example. What's the derivative of sine? Cosine. So was it just cosine of x down here? No, it was cosine of the original one, which was the inverse function. So we are done. This should be f inverse of x. It's not so much fun to write, but I think it's fun to say. 1 over f prime of f inverse of x. And if you take a look at the ln of x, the example that we did first, it actually follows this pattern. There's just some canceling. Downstairs, what's the derivative of ln of x? It's just 1 over x. Sorry, the 1 over we buy. It's always going to be a 1 over. How come it's just x? It shouldn't be. It should be more complicated, but there's some canceling that happens down there, just sort of behind the scenes. So I'd encourage you to think about that if you're interested. Real quick, we're just going to use this formula in one numerical example. So let's take a look at this thing right here. It says find the derivative of some inverse function. And then at the end, what are we going to plug in? X equals 3. That's what we're supposed to do, okay? Find the derivative of the inverse function and plug in x equals 3. And down here, I've given you a whole slew of data, most of which is useless. So what are we supposed to do? Well, I'm asking you for the derivative of some generic inverse function. The formula right up at the top of this page is the only formula we have at our disposal. So we're just going to use that formula. So let's try it. Equals 1 over f prime of f inverse of, and what number goes in there for the x? 3. That's the formula. And actually, once you've figured out, oh, I need to use that funny formula and written it down, the rest is almost trivial. It's going to be easy just to get some numbers out of this. But does everybody see how we came up with, like, it's just a matter of translating this circled purple thing into, oh, I got to use that formula. All right, so let's give this a shot. This says 1 over f prime of, f inverse of 3, it's in there, it's in the sea of numbers. F inverse of 3 is a third, right? You see it? So f inverse of 3 is a third, so that's what goes right there. So this problem is asking now for f prime of 3. Nope, sorry. You guys should tell me when I'm lying. What should it be? F prime of 1/3. Thank you. Equals 1 over. All right, f prime of a third. It's in there somewhere. Where is it? It's -5. This guy right here goes there. That's your answer. -1/5. Any questions on that one? Okay, we have 20 minutes. That may be enough time to do this group activity that follows. It goes on to the next page, and then there are answers. And I will just point out here, the first example is asking you for the derivative of log x. What's the derivative rule that we learned today that's kind of similar to this? ln of x. Derivative of ln of x is just 1 over x. You're going to find a slightly more complicated derivative for log of x, which is why we're not going to use log, we're going to use ln. So give this a shot. Again, work with your neighbors, and I'll come around and take any questions.